wobbly today, so yeah, I hope I don't fall in front of anybody. This big old thing on. Do what? Hurt my foot. Yep. Do what? No, but no. Actually, no, it wasn't CrossFit. It was walking on campus. So yeah, fell on a pothole. It was just grass, I thought, and so yeah. It's been a week and I haven't gotten better, so making myself stop doing too much on it. So, all right, chapter 16 is about rates. So we kind of briefly discussed that, talking about how chapter 15 was all about equilibrium, and it was about us looking at a reaction and being able to tell if it's favorable or not favorable. So that was the last thing we kind of did with our delta G. Okay, does anybody remember what, if delta G is negative, that means the reaction is spontaneous, and positive delta G is non-spontaneous. Okay, very good. All right, what's our delta G equation that relates delta G and enthalpy and...
Delta G equals delta H minus temperature delta S.
Very good. Okay, what's that H stand for? And what's the S stand for? Delta G is our Gibbs free energy that tells us spontaneity. Okay. Very good. All right. So we mentioned, and I'll even show it in here, that rates are totally different than whether it's spontaneous or not. Spontaneous means that it will happen and occur on its own, but it doesn't mean that it's fast. Okay, it doesn't matter if delta G is negative 50,000. Okay, it does not mean that it's fast. Okay, it means that it is spontaneous, so it will occur on its own. Okay. Kinetics is, like we just mentioned, the study of rates of chemical reactions and the mechanisms by which they undergo. Okay, we're not going to focus too much on mechanisms. That's really more for organic. Well, if you take that, you'll do that more later. Whoops. Okay. All right. Couple things here before we even get started, just to kind of lay it out, simplify it. Okay, rates is based on the concentration, so molarity, of the reactants. Okay, so that's what we're going to be looking at. Okay. Now you can look at, here it says products, but we're going to be looking at deriving what we call rate laws based on the concentration of the reactants. Okay, the reaction rate is basically the increase in concentration of product over a certain amount of time, right? That's the ideal situation, is that we have a reactant, it gets used up, meaning that bonds break, new bonds form, and we form our products. Okay, so that's the idea. But how fast is this is what we want to know. Okay, so how fast, bless you, will reactants be used up and products be formed? Okay, so this occurs everywhere. Okay, it's important to us in all areas or aspects of life. Okay, one would be in our own bodies. Okay, there are rates of reactions in our bodies that we need to be sustained at a certain rate. Okay, if they're too fast, this could lead to health problems. If those rates are too slow, this could lead to health problems. Okay, medications, okay, that's what's going on. Those medications are binding to enzymes in your body, and they're hopefully going to be pretty fast reactions that cure an illness or help you, your antibiotic, help you get over, whatever it might be. Okay, so that kind of goes along with illnesses. Preservation, so typically, if we want to preserve something, we want the rate of the reaction to be slower, right? So there are chemicals that we can add. Okay, you see this a lot nowadays. It's kind of a big organic versus processed foods, and how processed foods have chemicals, and they do. Okay, and these chemicals can also be radioactive and things like that. So there are chemicals that are put into foods and things to preserve them, okay, to slow down the rate. Okay, in industry, basically you want to develop materials at a useful and economic rate. Okay, if I go into and I try to present a reaction to a pharmaceutical company and I say, got this reaction, it's beautiful, it forms the product, just 99.9% yield, no side products, but it takes 3 days. Okay, that's not okay. That's not going to work. Okay, it has to be an efficient reaction, but it also has to be quick. Okay, not to say it has to be seconds, okay, but 3 days is too long in the industry world. That's going to take, lots of extra, hands, time. It needs to be quicker than that. So there's some cases where if that's the only option, maybe industry would do that. But typically they want a reaction to be done in hours. Okay, you don't want to be waiting around on a reaction for 3 days to finish. Okay. You also want to slow it down so that you want it to be slow enough so that you don't have lots of side reactions, so a lot of products that, side products that you don't want. And you also can't get too fast. One way that we can we can speed up reactions is heating them up. If you heat them up too much, then you're looking at dangerous, side effects here. So it can lead to explosion, especially if it's an exothermic reaction. Okay, so chapter 15, like we said, was thermodynamics. Will the reaction occur? Is it spontaneous? Will it occur on its own? Okay, now we're looking at how quick. Okay, so back to our example here. Okay, here's diamond. It will oxidize over time and form CO2. Okay, its delta G is negative 396. Okay, so its delta G tells us that this reaction is spontaneous or non-spontaneous. Spontaneous. However, this is very slow, very, very slow, millions of years. Okay. However, if you look here, this is an acid-base reaction. We have a proton, we have hydroxide, we have a positive, negative charge, and they instantaneously are attracted to each other. Okay. Its delta G is negative 79. Okay. It's lower than that. Doesn't matter, okay, with respect to rate. Okay. Both of these are spontaneous. That negative tells you spontaneous, but this one tells you, or actually doesn't tell you anything, but we know that this is fast. Okay, so it's showing you that delta G does not measure how fast a reaction is. No. Yep, that's exactly what I'm showing here. See, this one right here is a lot bigger than this, but this is extremely slow and this is extremely fast. So this is why it's a good example. No. Nope, not at all. It's measuring delta G. It's measuring, will the reaction occur on its own? Exactly. Exactly. Yep. The magnitude doesn't tell you how spontaneous. It's just telling you it is spontaneous. Okay, so that's why this is a good example and good questions, because this number, how big, how small it is, doesn't matter. We're just looking at that it's negative. Okay, and then with respect to rate, has nothing to do with rate. That's what I'm showing here. This is this is slow, but it has a large delta G. This is fast and it has a lower one. So there's no correlation between delta G and rate. Okay. Okay, so this is just kind of a hypothetical reaction. If you had A and B, those are your reactants, and you form C and D, okay, the little lowercase letters, that's just your coefficients, so whatever they might be. Okay, and the reaction rates are the rates at which the reactants disappear and products appear. So that's what we want. We want a reaction. We want to use up all of our reactants and form essentially our desired product in 100% efficiency or 100% yield. Okay, we know that's not usually the case, but that's what we want. Okay, so this is kind of looking at it like this. Okay, so you're up here starting at 1. That's the concentration that you would have. So if you had a 1 molar concentration of reactants, Okay? If they react over time, you're going to decrease the concentration, right? Okay. See how it never really gets all the way, all the way to zero. Okay, that's just life. It's never going to completely react. There's going to be, a minor amount that never will react. But at the same time, here's your products, C and D. So as you are decreasing reactants, you're forming products, right? Your reactants bonds are breaking, new bonds forming to form your products. Okay, so there's the products going up through there. Okay, we measure these in molarity there, moles per liter. Okay, and that's already what I mentioned. Okay, so a couple things here. Let's see if this works. All right, what we've mentioned here is we're concerned with reactant concentration. That's one thing that we know. Give me a marker. Oh. So rate, we're concerned with reactant concentration in molarity. Okay. If we have a simple, just one-step reaction here, okay, most of our reactions are not one step. They look like it to you because all you see is reactants and products. But even, I think it was last week that we talked about, there's a lot going on in between. It's not one step, it's usually 2 or 3 steps, can be as many as 10, who knows. Okay, but what you see is just point A to point B. Okay? If you did have a simple, one-step reaction, this is how we would write what we call a rate law expression. This is what you're going to learn to write today. Okay? A rate law expression, okay, is equal to, you just write out rate equals K, we'll talk about K in a second, times the concentration in brackets, okay, of, here it's A, because that's the only reactant we have, right? Okay. And this is going to be to some power, so we'll make that X, okay? Here it's understood that that is 1, because there's nothing there, okay? This is called the order of the reaction, okay? So get used to that term, okay? Concentration, once again, is in molarity. K is the specific rate constant. We'll get into more detail about it, but it's a constant, and we'll learn how to solve for it. But right now, you just write in K, okay? It's a constant, and if you look at it, if you increase K, what are you going to do to the rate, do you think? It's linear with the rate, right? So it's going to increase. So it does have a big factor in how fast a reaction is, okay? If the higher the K, the faster the rate. Okay, sometimes it's going to be a little confusing, but we'll just kind of stick to these first 2 bullet points. But if you have rate equals K times concentration A to the first power, okay, if you double the concentration, what are you going to do to the rate? You're going to speed it up, and you're going to double it, right? Okay, if you decrease the rate, decrease the concentration, so you half it, what are you going to do to the rate? You're going to half the rate, right? Okay. All right. I will say this once again. I know sometimes I repeat myself over and over, but there are a few points, usually in lectures, that I want to get across over and over to stick with you. Okay. This rate law, this is a rate law. This is a very simple one. Okay. It has to be determined experimentally. Okay. This right here, this order, okay, has to be determined experimentally. Okay. That means, okay, like I said up here, this is a trap for new students to kinetics. That's why I'm going over and over it, and will throughout today. That order, that X there, that's 1, or whether it could be 2, 3, 4, 5, 6, 7, 8, it could go on and on. Okay, that order is found experimentally. You cannot look at a balanced equation and think, oh, well, the coefficient in front of A is 1, so the order is 1. Okay, that does not work. It may coincidentally work one time. It may be the same or may not. Okay, but it will not work. That's not how it's found. Okay, so on Tuesday, what's today? Yeah, Tuesday, we'll actually look at experimental data and you'll see how you derive these and how you come up with the order. Okay, we're not going to get to that today, but the point is you cannot find this. Okay, you can look at a balanced equation, right, and you can tell what your reactants are. So that's, you can do that. But as far as the order, to what power, how significant is, your reactant? How much does it change the rates? That's what an order means. Okay, the higher this number, the more effect that concentration has, right? Okay, if I put a 3 there, okay, then that means my rate is going to, it's going to go, or it's going to be exponential, to that third power. So what you determine experimentally is how much does A, whatever that is, affect the rate. Okay? No, we're just using A it's just a general, we're not plugging anything in yet. We will in a few minutes. Okay, what this is right here, so if you're asked on your homework or test, whatever, derive a rate law expression. We don't know how to do that completely yet, but we're getting there. Okay, it can also be just called a rate law. It can also be called a rate equation or a rate expression. So don't get confused with the terms, okay? So there's different things that you can call this. Okay, but this right here, that's what we're talking about. Okay, that's our rate law expression or equation. Okay, I already mentioned this one because I wanted to say it over and over, but the order. Okay, some more terminology for kinetics. The order. Okay, that is this right here. Okay, there's 2 ways you can express order, so I will have to be specific. Okay, you can say that N2O5 is first order. Okay, that first comes because there you have an understood 1 there. Okay, we could say the same over here, right? If that was a 1, A has first order, effect. Then you can also, especially when you have more than one reactant here that's involved, you can also express this as the overall reaction, order. Okay, and that's the sum of all of the orders. Okay, so here we just have 1. So our overall order is also first order. Okay. Right, understood, just given 1, you can put it there if you want. So this reaction is first order with respect to, that's how I usually write it out, first order with respect to N2O5 and first order overall, because we only have 1 reactant and it's to the first. Here we have, that's our rate constant. Okay, notice, that's a 1 and that's a 2. They don't go together. You can't put a 2 here just because there's a 2 in the equation. And that's what I was talking about. It's the kind of the trap. Okay, this 1 this is experimentally found. Okay, and we'll look at how to do this later. Okay. All right. Say we had this. Okay, A and B are just generic. Okay. How you would correctly state all of the orders, if you're looking at number 1 for each reactant, you would say, this reaction is first order with respect to A and second order with respect to B. It is third order overall. Okay? You add up your exponents to get your overall order. Okay? And that order just tells you how much does this concentration, remember what's plugged in here is concentration of A and B, how much does that affect the rate? To what power? To what order does it affect? What do you mean? What do you mean together? Yes, you add, if say we had a C, a D, an E, and an F, like in the same bracket? I'm not sure what no, you write them in separate brackets. Yeah. And then you add up the orders, the exponents, to get your overall order.
Does it matter if you spell out or spell down? Does that matter?
Spell out what?
First or put 1 is to.
As long as I understand what to put. Good. Okay, here's another example. All right. This rate, law, expression, and the power of the orders has been experimentally given to us, determined and given. Okay? If you look here, we have 2 reactants. Okay? But if you notice, we only have 1 reactant in the rate law. So what does that tell us about hydroxide, OH minus? Do what? Yeah, it has no effect. So I could go in the lab, and this is really important to know, because you can go in the lab and say you're trying to make your reaction faster. If you go in there and you just keep pumping hydroxide into that reaction and you think it's going to speed it up, nope, not one bit. Okay, so it's important to know the reactants that are 0 order, that have no effect on the rate. Okay, so it's first order, okay, that's given to us, and understood 1 there. 0 order with respect to hydroxide because it's not in our rate law expression, right? Okay, and it's first order overall because we only have 1 there, and it's an understood 1. Okay, questions? Yes. Yeah, the CH3, CBR, so that's just really a, looks like that. That's a organic reagent. Yeah, it's 1 molecule. Okay, it's actually not a final example. I threw some more in here, but all right, look at this one. So we have nitrogen monoxide, oxygen, and we're given the rate law. Okay, so if we look at it, rate equals K times the concentration of our reactants to the power of their order. Okay, so the reaction is second order because there's a 2 there, right? Right. This time it just so happened that the 2 and there's a 2 there in the balanced equation and in your rate law, but they have nothing to do with each other. It just works out that way sometimes. Okay. All right, second order with respect to NO, first order with respect to oxygen, and it's third order overall. Okay, so once again, remember all these expressions are determined experimentally. At this point, they're given to us. Next week, you'll learn how to look at data and determine the rate law yourself. A little bit more on looking at how these concentrations and orders affect the rate. So we have a simple, just second order rate law expression. So we have A to the second power to the second order, okay, and we only have 1 reactant. So it happens the 2's match up. Okay. If we were to double the rate of the reaction, so we can double, we can triple, we can quadruple. What I do is I take, if it's going to double, then I put a 2 in there into the concentration, okay, just for 2 for double. And then to the second power, that means that the reaction rate is going to increase by a factor of 4. Okay, if we did the opposite and we halved the concentration, then it's going to decrease by a factor of 4. Okay. Okay. See your rate law expression there? Okay. If you were to take that concentration and double it, okay, so when I think double, you think of 2, right? So what you can do is put a 2 in there where the A was, and 2 squared is 4. That means the rate's going to increase by a factor of 4. Okay, here's some practice on, well, not yet. In a second, we'll have more practice on that. Okay, these are kind of long. I hope you can see them. I don't know why they did that, but all right, here's a couple other ones. So our rate law expression for this first one is K times the concentration of NO to the second power. It's second order with respect to NO and second order overall. All right, see if you agree with that second one there. They're hard to read. Let me try to. I know, it kept doing that to me. I made them on. See if I can. Oh, that didn't help. I can write them out if you can't see them. Okay, so it's telling us the rate is first order NO2. So if you had to write that out, you would write rate equals K. So say I didn't give you this rate equation at the bottom. Okay, so say I just told you that the rate is first order in NO2, so you would write out rate equals K. And what did I say, NO2? Okay, so you would do that. It's first order. You can write that there if you want. And then it says it's first order in fluorine. So if you had to transpose that yourself, that's what you would write. Okay. So it's second order overall. 1 plus 1 is 2. So the orders are the exponents. Okay, and once again, for like the fifth time, there's no way for us to predict these rate laws based on the equation, so we have to find them experimentally. Okay, so see what you can do with these. Let's just practice on being able to look at a rate equation that's given and think about what's going to happen to the rate. Okay, remember, we're talking about a chemical reaction. This is important because we need to know to what factor or how much is it going to increase or decrease the rate if we change variables, if we change concentration. So write out your answers for A, B, C, and D, and we'll go over them. Your answers? I think. Okay, if we triple A, so what do we think about when the number that we think about when we triple something? I think 3, right? Okay, we triple A, but we don't change anything else. So A is to the first power, right? So we're going to triple or increase by a factor of 3. Okay. For B, if we change it and we keep A and C the same, okay, B is to the second order, so it has more of an effect on the rate, right? So 3 squared is 9. It's going to increase by a factor of 9. Okay. C doesn't belong in the equation, right? Okay. And remember, A, B, and C, we're going to actually plug in actual chemicals, so this is just to kind of get you to see it before we do that. But okay, so it's not up there, so it's not going to affect the rate. Okay, what about if we triple all 3? Okay. So if we triple all 3, we're going to have 3 to the first power, and then 3 to the second power. So 3 times 3 to the second power is 27, right? Okay. And C doesn't affect, so we don't put that one in there. So it would increase by a factor of 27. Do what now? Just 3 to the first. If you triple it. Okay. So we're going to talk about some things that affect rate. We won't get to all of them. There's actually 4 main things. But before we get there, I just want to get a little bit of background of what has to happen for a reaction to occur. Okay. A reaction the molecules involved, so your reactants, they have to collide. Okay. So they've got to be close enough to each other to bump into each other for a reaction to occur. Okay. They not only have to collide, they have to collide with enough energy in order for them to break the bonds and form new ones. Okay. They also have to collide in a proper orientation. Okay, so you start thinking about all these things, it's kind of, to me anyways, kind of, I don't know, not a miracle, I don't guess, but that things actually work and that this actually happens all the time, okay, because it doesn't just happen on its own. They have to collision, they have to have enough energy, and they have to collide in a proper orientation. Okay. So if we look here, one thing we could do, and we'll talk even more about this, but just a kind of one that you might have already thought of, but if we can heat a reaction, okay, when you heat a reaction, what are you doing to those molecules? You're speeding them up, right? So you're going to get some more collision. And think about when we take, methane or natural gas and we have our oxygen, we have to light it with a match, right? We have to ignite it so that it will get over that activation barrier. Remember we talked about that in those diagrams? Okay, this is a spontaneous reaction, okay, but we have to get up over that activation barrier, and once we get there, remember it's like the ball you drop on top of a hill. It'll sustain by itself. Okay, so heating a lot of times will help us to speed up a reaction, but once again, we have to be careful. Okay, because yes, it speeds up and more bonds and more molecules will bump into each other, but we have to be careful that we don't heat it too much. Okay, so here are 3 ineffective collisions. So it shows you this is not an effective collision. Okay, it's a side-on. There's your bond in between. To the side, that's not going to be effective. Okay, what you actually have to have happen, and we talked some about orbitals in Chem 111, but your orbitals have to overlap. That's what a bond is. It's orbital overlap. Okay, and that right there, there's no orbital overlap. Okay, there all it did was switch the 2 around. That's not effective. Even this is not. Okay, yes, you have side-on overlap here, but you don't here. Okay, so that's an ineffective collision. All right. This is just one collision together, so it's not 3 different ones. Okay, this is an effective collision. Okay, you have side-on-side overlap. So think of X and Y being carbon, hydrogen, whatever. Okay, they have to side-on-side overlap. Okay, and when they do this, if we're trying to make an XY bond, so what we're trying to do is rearrange and bonds break, new bonds form. So what ends up happening is you form a bond here, and then these 2 break. Okay, and a lot more goes on. Of course, you have that's all about electrons, and we're not being very specific here, but okay, so those ideas go along with what we're about to talk about now. Okay. So we know that reactants need to collide with enough force, enough energy to break, form new products, and the right orientation. Okay, but there are 4 main factors that affect rates. You'll have to know these for sure for the exam. Okay, and we're only going to get really to 1 and start 2. That's all we're going to get to. Okay, the first one is the nature of the reactants. Okay, and this one is kind of really is a broad area, so we'll just give some examples is the best way to understand it. The second one is the concentration of the reactants, which that should be no surprise, right? That's in our rate law expressions is the concentration of the reactants, so it's going to have a huge effect on the rate. Okay, temperature is a pretty easy one there. Okay, typically if we increase temperature up to a given point, we're probably going to increase the rate because we're going to increase the number of bonds that are, or molecules that are bumping into each other. And then we're going to talk quite a bit about a catalyst. So I don't know if any of you ever heard of a catalyst before, but we'll talk about those. And catalysts, that's what they're used for. They speed up reactions. Okay, like I said, nature of reactants is best described by just talking about examples, okay, because it encompasses kind of a lot of different reacting properties. Okay, one is the physical state. Okay, so the rate of a reaction can be dependent on whether it's a solid, a liquid, or a gas, how fast it will react. Okay, we'll look at an example here in a second. Its accessibility. Okay, how accessible are those molecules? Okay, think about if you increase the surface area for which other reactants can come in and react, as you increase that surface area, you're going to increase the rate because there's more area for those molecules to react. Okay, so surface area is one. Okay, a strong acid, strong base, they have a extremely strong bond, electrostatic. Okay, so if there is a positive, so an acid we think of as having a positive charge and a base a negative, what do opposite charges do? They attract instantly, okay? Like that acid-base reaction I showed you in the beginning. Okay, so here's one. Powdered chalk and stick chalk react differently with hydrochloric acid. Which one do you think would react faster? I don't know. Why? The surface area, right? Exactly. So that's the example there. Okay. A puddle of gasoline burns pretty slow, thank goodness. Okay. But if you get gas and vapors, exactly. So that's a difference in the physical state between a liquid and a gas. Okay. Here's another pretty neat example. If you take magnesium and react it with steam or water vapor, okay. So the temperature here is 100 degrees, obviously, for the steam. And if you react this, it's an efficient reaction. It works. You form MgO, and you liberate hydrogen gas. Hang on just a second. Something weird's going on. Okay, there we go. Okay, but if you take magnesium and you react it with liquid water, it does nothing. Okay, so there's nothing that reacts that's perceptible to a chemist that they can see that happens. So the only difference is we had a gas here versus a liquid. Okay, so we had a quick reaction with a gas, and now we have no reaction when we use a liquid. Okay, so the only difference is our nature of the reactant. That's what we call it, difference between a solid and a liquid. Okay, number 2 is the biggest one that we'll spend the most time on, but like I said, we're not going to actually derive rate laws today. I mean, you have in a sense because you've been given the data, you've been given the orders, but we're actually going to find those orders next week. But it's pretty much understood here, bless you, okay, that concentration of our reactants has a huge effect, right? It's in our rate law expression, so we looked at if we doubled, if we tripled or whatever, the concentration of reactants. Okay, so this is just simplified, and this makes sense, should, hopefully already, just talking about collisions. Okay, the more collisions that you have, the higher the probability that you're going to form product faster, right? Okay, so if you just have, 2 reactants here, okay, you have 4 possible collisions. Okay, if you have more B, so B is just another reactant. So A and B are our reactants. If you add a little more B, then you have 6 different possible collisions. Okay, if you add a little more A and B, your concentration goes up. Okay, and now you have 9 different possible collisions. Okay, so the idea here is the more collisions that you can have, the higher the probability that the collisions are going to be effective. Okay, so that's why increasing your concentration will increase rate, because you increase the number of collisions that occur. We know that has to occur for bonds to break and new bonds to form. Okay, so that's exactly here. The more molecules that bump into each other perfectly, okay, then that is a true statement. They have to bump perfectly into each other for them to react. Okay, the faster the reaction will occur. So the higher the concentration, the more likely the reaction will happen at a faster rate. Okay, this is what we're going to be doing next week. So we're going to take experimental data, and we're going to read it, and we're going to decipher it, and we're going to be able to come up with our rate law and the orders based on the data that we would. So we're going to do this in the lab too. So you'll actually make your own table based on your experimental data in lab, okay, and do the same thing. Okay, so we're going to be able to look at it and come up with our rate expressions. Okay, so main thing here, really like 3 points, I guess, is that rate law expressions deal with the concentration of reactants. Nothing to do with our products in our rate laws. Okay? The order here, okay, this is based upon experimental data, okay, not on a chemical equation. Okay? I guess the third point is that we have to have collisions, effective collisions, in order for this to happen. And the more that we have effective collisions, the higher the concentrations is one way we can do that, then the faster the rate of the reaction. Okay, I want you to get out your, and I'll pull it up here in case you don't have it with you, but get out your chapter 15. We're way past that. Practice problems. I passed them out last week, I believe, so everybody should have one. So maybe I won't pull it up. Looks like this. Hopefully you've already been working on it. You can work on your delta G as well. 273. Yep, this is one. And then you also have your delta G sheet, if I can find it anywhere. Okay, you have book problems too, Hess's law. I make sure those are on the right page. But your delta G sheet looks like this. Okay, I didn't give one of these out. Okay, but work on any of these that you want to. Okay, this is your time to ask questions. It's not time to leave. This is time to work these problems. Ask me questions. Let me come around and try to help you on these if you need it. Which one? Okay. I may just do that one on the board. Okay. I'm going to do one real quick. Number 7 is the hardest one, I think, anyways. Okay, we didn't do one exactly like this in class, so that's why I'm do it real quick. Okay, number 7 on the chapter 15 practice problems, the multiple choice ones. Okay. All right, everybody look at number 7 on this right here. Okay. The difference here, okay, is that you're given grams of aluminum, but it wants to know how much, or calculate the heat for the aluminum oxide, okay? So you're going to have to go from grams to moles of aluminum, what you're given, to moles of aluminum oxide. Because look at your Al2O3 there, the delta HF, that is heat of formation that you're given there. Okay, that's for Al2O3, not for aluminum. Okay, so you've got to go to Al2O3 first. Okay, so if you take 8.17 grams, whatever periodic table I was using had a lot of numbers there. I don't know that you'd have that many, but okay, first thing is you take that grams of aluminum to moles. All right. Now look at your balanced equation. How many moles of aluminum do you have? 4. Okay, this number here, that just came off the periodic table. So grams cancel. Okay. And you're trying to go to aluminum oxide, right? Okay, and there's 2. Okay, so now you're in units of Al2O3. Okay. Okay, and I got that 1676 because that's our heat of formation. Okay, so that means, but we've already taken into account that we have 2 of them. Okay, so all we do is plug in that formation at the end so that our moles cancel. And then do the math, and I think end up with about, I don't know where I put my final answer. Is it 254? Yeah, it would be A, 254. All right, keep working, asking questions.